Okay, we'll revise what did we learn in our last session, Nitish.
Okay, ma'am.
Yes, tell me what and all did we learn in the last session?
We learned about all the quantum numbers, ma'am. And
Okay.
we did some sums about it, the artificial quantum number,
Hmm.
and all that, ma'am.
Okay. So I'm providing you, I'm going to provide you 3D Z square 1. Give the quantum numbers of this. Nitish, am I audible to you?
Ma'am?
Am I audible to you?
Yes, ma'am.
Yes. I'm asking you to write the quantum numbers for the specific representation.
Okay, ma'am. Ma'am, N is 3.
Okay.
So, L can be from 0 to 2, that is
Okay.
0, 1, 2.
Okay.
And now M can be from minus L to plus L, that is minus 2, minus 1, 0, 1, and 2, ma'am.
What about S then?
And S is 5, ma'am.
This is 5. How it's 5?
Sorry, ma'am. S can be plus half or minus half, ma'am.
So what you are providing me is for a general classification. I said N is 3. It can take the value from 0 to 2. And M can take the corresponding values. S can be plus of or minus of.
Yes,
What you are
ma'am.
providing me is the general values here, but that is not the question. The question was with respect to only 3D Z square. For this particular atomic orbital, what will be the quantum numbers? As you said,
L will be 2, ma'am.
uh, then M.
M will be minus 2 or plus 2, ma'am.
Mm-hmm. Check your classwork for dz square. What is the M value? Isn't it 0?
Yes, ma'am. 0, ma'am. Sorry, ma'am.
I wrote one electron here. So either it could be plus of or minus of. Yes. Okay, da?
Yes, ma'am.
So today we are going to learn about the nodes. In last class we did nodal planes. We completed it. Hope you remember.
Yes, ma'am.
And I said yes subshell or yes orbital. How many nodal planes it had?
Nothing, no, none, ma'am.
Zero nodal planes. Correct. And I say P subshell. How many nodal planes it had?
2, ma'am.
Two. Think and say
1, ma'am. 1, ma'am.
P subshell and asking. I didn't ask P orbital. What you're saying is for P orbital. When I say Px, the nodal plane could be either in Py or Pz. I said Py, it could be either in Px or Pz. When I say Pz, it could be either in Px or Py. So each orbital has one nodal plane. Therefore, P subshell will have how many nodal planes?
3, ma'am.
Three nodal planes it has got. Okay. What about D subshell?
6, ma'am.
Think and say. Each D orbital has how many nodal planes?
5, ma'am. 5, ma'am.
Planes. DXY, EYZ, and DZX. Each of them has two nodal planes, correct?
Yes, ma'am.
Dx square minus y square also has two nodal planes. Dz square is having zero nodal plane. Totally D subshell will have how many nodal planes?
8, ma'am.
Eight nodal planes. That's right. So this was with respect to nodal plane. Now we are going to learn about nodes. This was nodal plane. Now we are learning nodes. This is with respect to plane. The node itself tells you zero electron density. There is no electron density. When I say nodal plane, I am talking with respect to the plane in which zero electron density is there. Right?
Yes, ma'am.
When I said a node, it is not about a plane, it is about a particular region in which no electron density is there. It's called as nodes. Okay, pa?
Understood, ma'am.
Yes. So we are looking at the nodes now. Now there are different types of nodes we have. The first type of node is called as radial node. Called as radial node. So what is the formula to calculate the radial node? Which is given by n minus L minus 1. A radial node will also be called a spherical node. It should also be called as nodal region. Specific, not specifyingly, just I say nodal region, which is also called as radial node, also known as spherical node, also known as nodal region. The formula is n minus L minus 1. Now the next type of node is called as angular node.
Ma'am, can you go down?
Sorry,
Can you go down a bit, ma'am?
you want me to repeat it?
No, ma'am. Can you scroll down?
Scroll down. Now, okay.
Okay, ma'am.
Angular node is given by the symbol L here. Radial node is given by n minus L minus 1. Angular node is given by the symbol L here. Okay. So we are going to understand what is this node, how do I identify it? Let me consider n is equal to 1. What is the L value? 0. What is the M value? 0. So what is your orbital right now? 1 is Nitish?
Yes, sir.
Ma'am.
Yes.
Uh,
Can you hear me? Can you hear me, da, both of you?
Yes, ma'am.
Right. I'm just recording the session. Wait a minute. Yes. So we are discussing about the nodes here. For that, initially they drew the graph between psi and r. Then they started drawing the graph between psi square and r. What is this psi? Psi is nothing but called as wave function. See, consider the electron is there, which is moving around the nucleus like a wave like this. What is its function with respect to spin of it, with respect to momentum of it, with respect to energy of it? What is the function of this wave? That is what is called as psi. So when they tried to attempt to draw the graph between psi versus r, this part tells you about the distance from the nucleus to the electron. Consider the electron is here moving like a wave. What is the distance that is traveling? That is called as r. So the first graph was between psi and r. The second graph was between psi square and r. We are going to learn why did they change from psi to psi square at first. Consider this graph. Psi is also telling you about the probability of finding the electron. Look at this one here. Look at this one here. As you see in the x-axis, I'm moving away from the nucleus. The graph shows you when you are very close to the nucleus, you find maximum electron density. That's what it shows. It says that if I'm very close to the nucleus only, the electrons are more. Is that true? It tells you if the nucleus is there, the electron is like this. Is that possible?
No, ma'am.
No, it's not possible. Ruther or Ford also suggested the same thing. No, it's not possible. There's quite a lot of distance between the nucleus with respect to your atomic orbital electron here. Isn't it? We found it was 10 power minus 15 meter radius of the nucleus, and the radius of the atomic radius was 10 power minus 10 meter. Such a large difference is there between them, distance is there. And how can we expect the electron will be very close to the nucleus? So this graph was wrong. This graph was wrong. The graph was drawn between one or the oneness orbital. They are trying to draw that. Okay. When they try to draw the same graph for 2p orbitals, they found like this. What did they find? The first mistake is it was close to the nucleus. That itself was a mistake here. The second mistake is that you can see the electron density is moving in the negative axis. Can you see this?
Yes, ma'am.
So can you? What does it suggest? The electron is interior of the nucleus. Is that possible?
No, ma'am.
This is not also possible. So therefore, this graph was also not just it was wrong for the closeness with respect to nucleus, but was also showing you the negative probability distribution with respect to the nucleus. So this was also wrong. Okay, right. So what they did was they went to the next graph between psi square and r. Because this was negative, if I square the negative, that means negative into negative will become positive. I can eliminate this negative axis now. So they went for squaring it. Okay. what was the result? By squaring it, I think it has not come till now. You can see the graph went up. There was nothing in the negative axis. So that was one thing, nothing in negative axis. But you can find still the electron is very close to nucleus. So that is also wrong, isn't it?
Yes, ma'am.
The problem got solved with respect to the negative axis, but still the problem existed as the electron was very close to the nucleus. So that was also not correct. So they tried to move it further. And they assumed that there is a nucleus. If I say there is electronic cloud in the first shell, definitely in between this place, there's a lot of empty spaces available. So they assume that there is a node, there is an empty space here between the nucleus and the next orbital, or between the subsequent orbitals. I repeat, there is a nucleus here. So there should be something spherically around here, which is a node. There is no electron here. It is having zero electron density here. There is no electron at all. And after that only there should be an orbital or orbit where the electron will be available. For that, they introduced 4 pi r square NL. We are not going to dig deep into this segment here because which goes for Master of Physics here. 4 pi r square NL with R, they found that the two problems were solved. Looking at the graph of 1s atomic orbital, you can see nearing the nucleus, there is least electron density very close to the nucleus. First thing they are able to identify. Okay, is this correct?
Yes, ma'am.
Yes, this is correct. So one problem is got solved. What is the next problem? There is nothing in the negative axis. No negative axis is there. So another problem also got solved. So what you are seeing right now is showing you the maximum probability of finding the electron around the nucleus at certain distance from the nucleus. This maxima tells you about maximum probability of finding the electron away from nucleus at certain distance. Clear path?
Yes, ma'am.
So we discussed about three types of curves here. One was between psi versus r. Another was between psi square versus r. Both of them had the trouble. Even though in psi square there was nothing negative, but still I found the electron is very close to the nucleus. So to remove it, he assumed the next y-axis 4 pi r square NL. This NL tells you it is with respect to your principal quantum number and azimuthal quantum number. When you draw the graph for 1 x,
Ma'am.
yes, pass.
And what is that formula, ma'am?
This formula is telling you about the radial probability distribution.
Is it related to psi, ma'am?
Yeah, it is related to psi only. For psi, this is psi square tells you it is r square NL. Here I am introducing a spherical kind of a thing. And I introduce 4 pi r square. This tells that there is something quite available. That means There is a lot of space around the nucleus and the next orbital or between the different orbitals. A space is there. That's what the number shows.
Okay, ma'am.
Okay, so this is for oneness. Now let us understand with the formula that we learned. We learned the formula radial node is equal to n minus L minus 1, correct? Let us
Yes, ma'am.
substitute for this oneness orbital. What is the n value here?
1, ma'am.
1. Whatever number I have written in front becomes your n value, 1. Minus, what is your L value here?
0, ma'am.
0. Minus 1. What's your answer? 0. It says that there is no node at all. Look at this here. Since I started away from the nucleus, you can see I'm having maxima only. And it just goes on. It didn't touch the axis at all. It didn't go and touch the axis like this. Isn't it?
Yes, ma'am.
So that I'm able to understand from the radial node. Similarly, calculate your angular node is given by the value L. L is nothing but 0. So the angular node is also 0 here. It means that there is no particular angle away from the nucleus where I will not see any electron at all. Because in S, I can see this completely symmetrically around.
Okay, ma'am.
Now let us consider for 2S.
Ma'am,
Ah,
what's the difference between angular node and radial node?
angular node is given only with respect to the angle part, L value. And spherical node, you introduce principal quantum number also.
Okay, ma'am.
Do you guys have learned about this electronic configuration? How do you write 1s to 2s to all the steps?
Yes, ma'am. Like in ninth, ma'am.
Do you want me to repeat it or you know it already?
We know it, ma'am.
Kavish?
Yes, ma'am.
Okay. So I'm talking about 2s right now. Calculate your radial node. 2 minus 0 minus 1. What's your answer? 1. So what does this suggest you? It suggests that there is one radial node here, correct? So let me draw the diagram here. 4 pi r square nl versus r. The graph shows you like this. What does it suggest? The first
Ma'am,
peak, tell me.
L can also be 1, right, ma'am?
Day is yesterday.
Oh, sorry, ma'am.
The first peak shows you it is 1s. The second peak shows you it is 2s. What does it mean? Ma'am, I have my nucleus. The first one was 1s. The second one is 2s. That's what it shows. So here I can see there is a node that is existing between this orbital 1s and 2s, isn't it?
Yes, ma'am.
And that's what is the number 1 shows you.
Okay,
Similarly, the
ma'am.
peak also shows you. Ma'am, I had 1s. I had 2s. You can see there is an bare minima that's going there. What does it show you? There is a node that is available in between them. The electron was present in 1s, and the electron is present only in the 2s. There is a node that is available in between them. Okay.
Okay, ma'am.
Also, you can witness this. The maxima of 2s is greater than 1s. It's because as you move away from the nucleus, as the shell increases, there's a lot of having a lot of orbitals there. As you increase the number of orbitals, certainly more number of electrons could be there. So the probability of electron is also more there. Understood, Ra?
Yes, ma'am.
Right. Let us calculate for 2p.
Yes, ma'am.
Kavish, go on.
Yes.
Ma'am, is it 0?
Very good. Just substitute your value n minus L minus 1. N is 2 here. And L value for P is 1. So it is 0. What do you understand? I understand that there is no 1p at all. Is there a chance that you have 1p?
No, ma'am.
No, because when n becomes 1, what value L can take? Only 0 it can take. How can it become, how can it be 1 to become P? Not possible. So I understand here in 2p, there is only one peak here for 2p. There is no 1p. In this case, in the previous example, you see there is 1s and then 2s. So only you add a node between. But here it is only 1p. So it's only 2p. You can't have 1p at all. And that means there is no node at all. What you are drawing right now is called as radial distribution curve. RDC. Okay. So go on. 3p.
Yes, ma'am.
How many peaks you expect?
1, ma'am.
1. That's right. I have 2p and 3p. Correct? And I'll have
Yes, ma'am.
one node in between. 3D. What about 3D?
0, ma'am.
0. That's right. Using the formula for 3D, n minus L minus 1. N is 3, L is 2, it's 0. Of course. Do you have any 1D and 2Ds?
Not possible, ma'am.
Not possible. Because when n is equal to 3 only, I can have L is equal to 2. Then only I can have D. So therefore, here also I have just one single thing, which is 3D here. Cleared up?
Yes, ma'am.
And that's what we are seeing right now in this page here. We discussed right now. Oneness. I don't have any node at all. There is no node. There is no nodal plane either. This is my maxima. When I said n is 2, I am having 2s and 2p. Two possibilities are there. For 2s, I have one node is there. Correct or not? Between 1s and 2s. And in 2p, I have no node at all. Do you understand, Kavish?
Yes.
When I say n is equal to 3, I have three possibilities 0, 1, and 2. 3s, 3p, 3d. For 3s, I have a node between 1s, 2s, 2s, 3s. For 3p, I have a node between 2p and 3p. For 3D, I don't have a node at all. Clear till this?
Yes.
Okay, right. We'll solve certain questions now. Look at the question. In our graph, we wrote 4 pi r square nl, right? This r square nl will also be addressed as psi square. That's what they have mentioned. Shall we solve it? Am I audible?
Ma'am, yes,
Hmm.
ma'am.
So they said n is equal to 3, L is equal to 1. Which orbital it is?
3p, ma'am.
It is 3p orbital, right? In 3p, how many nodes you will have? One node you will have. Substitute formula n minus L minus 1, n is 3, L for p is 1, and this is 1. So how much you have? 1. Among the graph, this is not having any nodes at all. Here I am having 2 nodes. Here, in both the cases, I am having 2 nodes. But what did I tell you? As you move away from the nucleus, the electron density should increase. But here you are saying you are decreasing, right? So it
Yes,
can't be
ma'am.
my option. So this is the correct option.
Till when is the class, ma'am?
What, ma?
Till when is the class, ma'am?
1 hour.
Okay,
Today
ma'am.
evening we'll do 1 hour. Na? Instead, I thought why to take it till evening. You people are having
Okay,
holiday
ma'am.
early. Na? So I thought let's do it now. Okay. Let's go for the next question. Don't look at the solution. Look at the question and solve it. Okay, the radial distribution curve for 2s atomic orbital has one trough representing a radial node.
Ma'am?
Yes,
Ma'am, is all three correct?
the number of angle nodes cannot be found using the radial distribution curve. Is that correct?
Yes, ma'am.
The radial probability distribution curves for 2s atomic orbital as one representing a radial node. Is that correct? Yes. Correct, na? The radial
Yes, ma'am.
probability distribution curve for 2s, 3p, 4d are similar in shape. What about their shape here? What about the shape here? Yeah, I'm having the same kind of a shape. Only correct or not? Children, am I audible here?
Yes, ma'am. Audible, ma'am.
Yes. The number of angular nodes cannot be found using the radial distribution curve. Radial distribution curve is only talking about the radial node here,
Yes,
isn't
ma'am.
it?
What's the answer for that question, ma'am?
1 and 2. This you can't
Okay,
find.
ma'am.
The radial probability distribution curve obtained for an orbital of wave function valence electron of an alkaline earth metal atom has 4 peaks. Asking you which metal it could be. Huh? They said it is valence electron. Okay. And they said it is alkaline earth metals. Correct? So we know in
Yes,
alkaline earth metals, generally they have the configuration NS2. So definitely they are talking about s orbitals only. So what am I will I have? Calcium. They said it's 4 peaks here. So
yes, ma'am.
1s, 2s, 3s, and 4s. Correct?
Yes, ma'am. Correct.
So I should be having a peak between here, a peak between here, a peak between here, huh? And another peak should have been there, right? Then only let's say 4 peaks here. Correct, Appa? Am I audible, Raf, for both?
Yes, ma'am. Audible, ma'am.
Okay, right. Now let's go for the next question. Considering the radial distribution diagram, which of the following matching curves do you have with respect to the orbital here? Given 3 peaks here, curve 1, curve 2, curve 3, match it up.
One is 3P, ma'am.
1 is 3p. I have 2p and
Three,
3p.
2 is 3D, ma'am.
2 is 3d. Okay,
3 is 3, 2, 3, yes, ma'am.
very good. That's right. Kavish, are you there?
Yes, ma'am.
Did you understand why he says it's 2p, 3D, and 3s here?
Yes.
No. Because you're not interacting at all. Please be interactive here.
Yes.
Because in an online session, if you're not interactive, I may not know whether you understood it or not.
Yes.
So we need not discuss these questions, isn't it?
Yes, ma'am.
I'll go for this question then.
Ma'am, option C, ma'am.
Why?
And because M cannot be 1, ma'am. M can only be plus negative or minus negative.
I don't understand. What is it? L is 1. M could be plus 1, 0, or minus 1. Yeah, you are saying plus 1. Now, why did you say it's wrong?
Oh, sorry.
In all the cases, it's possible when you look at A. I'm saying the spin quantum number is 0. Have you ever seen spin quantum number is 0 here?
No, ma'am.
So, it's not possible. You can see representing as ML and MS. This is with respect to your L value here. And this is your spin quantum number here. Okay. So, we will be
Okay, ma'am.
addressing a term called the spin magnetic moment. Learn the formula now for this. Okay, right. Let's go for this question.
Oh, what is a period, ma'am?
In the periodic table, the horizontal lines are called as periods. I have hydrogen, I have helium, I have lithium. The horizontal ones are called as periods. And the vertical columns are called as groups.
Okay.
Okay. So they're asking you if each orbital can hold a maximum of 3 electrons, the number of elements in the second period. Usually, every single orbital, each orbital can take maximum how many electrons? 2 electrons only it can take, isn't it? I think you should have learned all
Yes,
these
ma'am.
things because as you told, you know electronic configuration, you should have learned it. 2 electrons is maximum, but now they are saying if it is going to have 3, then what is the case? When I go for the second period, when I go for the second, when I go for the second period, what are the things that are available? Second period says that the n is equal to 2. What are the orbitals that are available in n is equal to 2? 2s and 2p. Both of you, can you understand what I'm saying? Hello? Nitish and Kavish, can you hear me?
Yes, ma'am.
I'm discussing about the second period. In second period, what do you mean by second period? It means it is, I'm talking about n is equal to 2. That is called a second period. Second shell corresponds to second period. Okay. In second period, Or in the second shell, how many orbitals are available for us? Subshells are available. Have you learnt about this?
Yes, ma'am.
I only taught you now. When n is equal to 1,
Yes, ma'am.
L is equal to 0. So only 1s can be there. And n is equal to 2. L can be 0 and 1. So it could be 2s as well as 2p. Now, initially,
Yes, ma'am.
usually I will have only 2 electrons. So S can take 2 electrons. Each p can take 2 electrons. So totally 6. So I will have 8. But now what they are saying? Each orbital can, if it can take 3 electrons, then what is the possibility? And this is 3 here. And what about here? I'm having 3 orbitals, isn't it? So each can take 3. So totally how many I have? 12 I have. Understood, Rob?
Yes, ma'am. Understand, ma'am.
Avish, did you
Yes.
understand?
Yes, ma'am.
Yes. Let's go for the next question. They're asking us, when could you have this G subshell? In this one, I said 0, 0 and 1 is there. In n is equal to 2, it's SP. And n is equal to 3, it is 0, 1, 2, so it's SPD. Then when I said n is equal to 4, you said n 0, 1, 2, 3. So SPDS. Only when n is equal to 5, I get 0, 1, 2, 3, 4. So after F, the next subshell is G subshell. So in the fifth energy level only, I can have G subshell.
Understood, ma'am.
We are learning about the spin magnetic moment here. In other words, we call it a spin only magnetic moment. It is given by the formula square root of n into n plus 2, where n stands for number of unpaired electron in that element. So they are asking you to calculate the spin only magnetic moment of Fe3 cluster. Iron takes atomic number of 26. Which block element it is? Which block element is iron? Hello? Which block
Um,
da? Huh? I can't hear you, Nitish. Which block ka?
I'm D block, ma'am.
D block, that's right. It's a D block element. When we do further, I would really definitely want you to memorize the complete set of the periodic table. But for now, you need to know at least the 3D series, the first transition series of the D block element. Titanium, vanadium, chromium, manganese, iron, then completed. You guys know it?
Only a bit, ma'am.
Only a bit.
Cobalt,
Calcium,
nickel.
correct. Cobalt, nickel, correct. Copper and zinc. So from calcium we started. So calcium is called as bridging element here. From there only I start my first transition series. It is called as 3D series. Here. Let's fill the configuration of scandium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Correct? As I said, you learned it already. I'm just writing it. Correct, Appa? Hello. Kavish, do you know how to
Yes,
write
ma'am.
this configuration?
What, ma'am?
Do you know how to write this configuration?
For what, ma'am?
Scandium, I wrote it for scandium. Na?
Oh, yes.
Because I can't take it as such. Na? People say suddenly I don't know. And she just wrote it means. You know, I can process it. I can proceed. You know it, right?
Yes.
Yes, ma'am.
So with that, they are asking me for the magnetic moment of Fe3 plus. Same way, let's write for iron here. But 26 it is. So what is it? 4 is to 3d6. 3 plus it is. You can see this is in the fourth shell. This is in the fourth shell. So what do I, how can I remove, from where can I remove the electron at first? Only from here I can start removing. How many electrons should I remove? 3 electron I will remove. So 2 from here and 1 from here. So totally 3 electron I have removed. Now what is its configuration? 3d5. N stands for number of unpaired electrons. So I substitute the N value here, which is 5. Okay. And the unit is called as Bohr magneton. BM.
Okay, ma'am.
The next one is called as orbital angular momentum, which is given by the formula square root of L into L plus 1 h bar. And h bar is nothing but h by 2 pi. Okay, for the d electron, they are asking us. For d, what is the value of L? 2. Substitute to get an answer.
Okay, ma'am.
Okay. Let's go for this question. Number of electron in sulfur having n plus L value has to be 3. Don't look at the solution. Do it by yourself.
Ma'am.
Ah,
Ma'am, for the orbit angular momentum, is it root of L into L plus 1 into H?
h bar.
Okay, ma'am.
Okay, let's go for this question. Number of electron sulfur atom having n plus L values to be 3. So what are the possibilities that I can have? N could be 2 and L could be 1, right? Is there any other
Yes,
possibility that
ma'am.
you have?
No other possibility.
No other possibility because, ma'am, yeah, I can go for several possibilities. I can say 1 plus 2, I can say 0 plus 3, I can say 3 plus 0. Any possibilities are there, isn't it?
Yes, ma'am.
So I am finding out among them which could be my good possibilities here. 1 plus 2 is not at all possible because n, if it is 1, L should be definitely less than 1. But I said is 3, 2, not possible. Similarly, this combination is also not possible. So what are the two combinations that are possible? 2 comma
2,
1 and
comma
3.
1 and 3, comma 0.
Exactly. So 2 comma 1 says it is 2 and 1 says it is P. 3 comma 0 says it is 3 and 0 says it is yes. So two possibilities I have, 2P and 3S. Am I right?
Yes, ma'am.
Yeah. So now the question is about how many electrons it can have. So I know P can take 6 electrons and S can take maximum 2 electrons. So totally how many electrons it can have? 8 electrons it can have. right? Let's go for this question.
Okay, ma'am. Yes, ma'am.
It is an advanced question, I guess. It is an JEE advanced question. Hydrogen-like species lithium plus is in a spherically symmetrical state S1 with one radial node. So they are giving you a clue about this S1. They said it's spherically symmetrical. That is my first clue. So what do I understand? Definitely it's S subshell. It is having one radial node. Which S subshell will have only one radial node?
2s, ma'am.
2S. Just now learnt 1S and 2S. This will have one radial node, right? 2S will have one radial
Yes,
node.
ma'am.
So the
Yes,
state
ma'am.
S1 is 2S. Correct?
Yes, ma'am.
Yes. Next. And upon absorbing the light, the ion undergoes transition to a state S2. So from 2S, it is moving to some state S2. Since it is absorbing light, definitely S2 will be higher energy level only.
Yes, ma'am.
The state S2 has one radial node. It is having one radial node, and it is equal. Its energy is equal to the ground state energy of the hydrogen core. So they are trying to relate with the Bohr's concept here. Two clues you have got. One it is having one radial node, right? And the another thing is that its energy is equal to ground state energy of the hydrogen. So what is the ground state energy of the hydrogen? Minus 13.6. Am I right?
Yes, ma'am.
You learned it in the Bohr's concept. Energy of hydrogen minus 13.6 Z square by N square. Z is 1, N is 1, so it is minus 13.6. They are saying the energy of this lithium when it went to the highest energy level matches with this value. So I'm trying to find out what it could be. So minus 13.6, when Z and N becomes equal only, it will become equal. Am I right?
Yes, ma'am.
Yes or no? I'm checking what are
Yes,
the
ma'am.
what value I could have. Z value is 3, I know.
3D, ma'am. I think so.
And N value should be 3. Then only it could can cancel here.
Yes, ma'am.
Okay. So then it should be definitely be in the third shell. That's my understanding. And this is having one radial node.
4D, ma'am. 4D.
Right.
4D.
You said 3 da. N is 3. How can it be 4D?
Sorry, ma'am.
Tell me now. Yeah, I said N is 3. And they are telling it is having one radial node. What is the
3P,
possibility?
ma'am.
3P. Correct. Because when N is 3, you have a possibility of having 3S and 3P. 3S will have two radial nodes between 2S and 3S, right? 1S,
Yes, ma'am.
2S, and 3S. I have two radial nodes. So 3S is not possible. What about 3P? 2P and 3P.
Impossible, ma'am. Only one node.
So therefore it has went to 3P then. That's my understanding. Okay.
Okay, ma'am.
Okay, pa? Yes. So in today's session, we have learnt about the radial distribution curves, psi, psi square, 4 pi r square, and psi square. So three different curves of we learned. We saw why the psi and psi square was wrong and what made this 4 pi r square NL to be right. And the final one that we saw was radial distribution curves, RDC, also called as probable distribution, radial distribution curves. Okay. So we saw with respect to it how to calculate the radial node, angular node. How do I find from the graph what is the orbital that is present in? And we solved certain questions from the quantum mechanics aspect. Okay.
Yes, ma'am.
Right. We'll wind our session with this. Catch you in our next session.
Thank you, ma'am.